Hello and welcome to this film, which is all about hybrid orbitals and what we need to know about them for the IB higher level chemistry course. I suppose we're kind of coming into the home straight of the bonding topic now. We've really just got to talk about hybrid orbitals and about resonance, and it can become a little bit abstract. So more than ever, I suppose, if there's stuff that you're not getting the first time you see it, then it's worth watching it again. And if that still doesn't make sense, please make sure that you come and talk to me about it, or find out about it from somewhere else so that you can maybe have it expressed to you in a slightly different way. Anyway, hopefully by the end of this film you're going to see some evidence for the idea that there might be some kind of mixing of orbitals going on when atoms form bonds with one another, and you're going to understand why we call these hybrid orbitals the names that we call them, and you're going to see if you can look at the bond angles present. So again, we're kind of falling back on what we know about shapes. We're going to look at the bond angles that are present to determine what type of hybrid orbitals there are in a molecule or in a particular bond. Right, well, I suppose the first question to ask is that what if atoms use their usual orbitals to form bonds? Okay, so in methane, which remember you might not be very familiar with if you haven't done the organic topic yet, but anyway, there's its formula, CH4. If carbon was using its outer shell electrons, which it does, we're kind of used to it, the idea that it's sharing its outer shell electrons with hydrogens to form bonds, then it would be using electrons from its 2s orbital and from two of its 2p orbitals. The slightly odd thing about that, or the outcome of that, I suppose, would be that we'd end up with two bonds that looked kind of similar, because hydrogen would be overlapping with this electron and this electron, which are in a nice spherical orbital, and two of the hydrogens might be overlapping with, well, one might be overlapping with this p orbital and one with the other. And what we might remember about these notations here, px, py and pz, is that these are lying on the x, y and z axes. So in other words, these are 90 degrees apart from one another. Okay, so in other words, we might expect two of the bonds to be 90 degrees apart and the other two to be, I don't know, something to do with this sphere. But certainly we wouldn't expect to see four exactly the same bonds. But that is exactly what we see. As we know, methane, as this marvellous diagram, which I certainly didn't draw, shows, methane forms this perfectly symmetrical tetrahedral arrangement where all the bonds are exactly the same length and all the bonds are exactly the same angle apart from one another. So clearly carbon can't be using its usual orbitals to overlap with hydrogen orbitals, because that's what atoms do to make bonds. They overlap their orbitals when they share electrons. So it clearly can't be carbon's kind of bog standard orbitals that are being used to make these bonds. How can we explain this? Well, either it takes a moment of genius to kind of come up with this idea that carbon is mixing orbitals in order to find these tetrahedral ones, or it takes someone who's very, very good at quantum mechanics and maths to be able to combine the wave functions of these orbitals. Don't worry, you don't have to do that for now, to come up with some new orbitals. Now, the conservation of energy, or the law of the conservation of energy, says that if we take four orbitals and mix them together, we're going to end up with four orbitals. What might we call these four orbitals that we've made by mixing these orbitals? Well, we took one s and three p's, so why don't we call them sp3 orbitals? Because that will show what we mixed to make them. And the maths behind the kind of the quantum mechanics here would tell us that if we did this, not only would we form four sp3 orbitals with this particular shape, which is kind of, I suppose, a bit of a hybrid between these, they'd also, these four orbitals, be 109.5 degrees apart from one another, which is, you know, I mean, remarkable sort of discovery if you're looking at the molecule and going, wow, okay, so this bizarre theory of quantum mechanics is actually explaining why I've got the bond angles that I'm observing in a molecule. So it's really very powerful, even though a lot of people took a lot of convincing that it actually made any sense whatsoever. Anyway, so we've mixed some orbitals together to form some new hybrid orbitals, right? So these hybrid orbitals are ones that we formed by mixing other orbitals together. Now there's other kind of hybrids too. We've looked at sp3. Ethene has a different type of hybrid. Ethene mixes one of its s orbitals with two of its p orbitals and leaves one of the p orbitals unchanged. So 3 orbitals have been mixed. We end up with 3 orbitals and 1 left over, and because these orbitals were made of s and 2 p's, they're called sp2 hybrids. Once again, they're hybrids because they were made of orbitals that were mixed together. And guess what? The maths again tells us something that we've already observed, which is that these sp2 hybrid orbitals will adopt a geometry that is trigonal planar. They'll be 120 degrees apart, and that's precisely the bond angle that we measure in ethene. So all the pieces are kind of fitting together if we're trying to, suggest that quantum mechanics is a good way of looking at things. Okay, so anyway, leaving the quantum mechanics to one side, the important point from this slide is that if you take one s orbital and mix it with 2 p orbitals, you'll be left with a p orbital, and you'll have 1, 2, 3 sp2 hybrids. Now there's sp3, there's also sp2. You might not be surprised to see that you can mix one s orbital with one p orbital and end up with something called sp hybrid orbitals. You mix 2 orbitals to make them, so there must have been 2 orbitals resulting. These orbitals happen to have, the quantum mechanical theory tells us, and if we do the number crunching, they happen to have a geometry of 180 degrees apart, and that explains why we've got a 180 degree bond angle in ethine, which we'd be able to predict just by drawing an electron dot diagram, because there's 2 charge centers around this carbon. Okay, so we'd end up with a 180 degree bond angle. Okay, it's important to realize that these orbitals here are hybrids. They were made by mixing these orbitals here, and because we mixed one of the s's with one of the p's, remember carbon has 1s and 3 p orbitals in its second shell, we've got 2 unused p orbitals. And this is going to be really important in the next film when we start looking at examples of where hybridization is used to make bonds. Okay, so I suppose, having been introduced to this for the first time and maybe wondering, well, okay, what do I need to know about all this stuff? Really, the key points from this film are, we've explained what hybridization is, and that is quite simply, if you get asked what's hybridization in an exam, you just say it's the mixing of orbitals. What do the names tell us? The names tell us what orbitals were mixed to get those hybrid orbitals. Okay, so in other words, you ought to be able to decide what orbitals an atom is using in order to make its hybrids, and also what orbitals that leaves you with that you haven't yet mixed. And we're also looking at how we can spot each kind of hybridization, and remember the way we did that was by looking at the bond angles. Okay, so 109.5 degrees, that tetrahedral bond angle, suggested we had sp3 hybridization. If we had a 120 degree bond angle, we were thinking, oh right, that must be sp2. If we had a 180 degree bond angle, that's telling us we've got sp hybrids in around that atom forming the bonds. Okay, so what were we trying to achieve by the end of this film? We were trying to get some evidence for the idea that atoms might mix orbitals when forming bonds. Okay, we looked at bond angles and bond lengths to decide that. We looked at the names of hybrid orbitals and what we might determine from their bond angles, and we might look at the bond angles in a molecule to quickly be able to go, oh right, that must have those sort of hybrids. Okay, if any of that doesn't make sense, which I suspect it might not because it's quite an abstract topic, as I said at the start, please feel free to comment. Please feel free to ask questions, whether that be through YouTube or in person.